All right, so we're going to continue on with derivatives. So this will be kind of the third part of the sort of basic rules of derivatives that we've been seeing. Before we saw derivatives in the context of the limit definition of the derivative. But today we're actually going to go away from that. We're going to start doing derivatives in a much more simple way. And so we'll get into that. First, I want to start talking about some notation. We've basically just been using this notation f prime of x to denote a derivative, but there are in fact other notations that you can use, whether it be based on your personal preference or the situation at hand. There's different uses for different notations. So let's go ahead and look at these. So can sort of split these up into four parts here. Each of these are a completely different look to them, but they all mean the same exact thing. They all mean the derivative of f, whatever our function f may be. And so we've seen the classic, we've seen the classic f prime of x up here in the top left. So that's good. We know what that looks like. We've seen this over and over. Another way that you could write this is df dx. And so again, I'll say that again because that's how it's stated verbally, df dx. Sometimes df over dx, but usually if you say df dx, people kind of know what you mean by there. And all that's saying, it's just a slightly different look to it than f prime of x. It's just saying, hey, I'm taking a derivative of f, and the variable that I'm taking that derivative with respect to is x, just like I had that here. I have my function f, and this prime tells me that I'm taking a derivative of f, and the x is the variable that I'm taking the derivative with respect to. Likewise, very similar to df dx, if instead you called your function y instead of f, a lot of times we'll write out a function as y equals x squared instead of f of x equals x squared. In that case, we might say dy dx. And again, this has a very specific use for it. Or I shouldn't say specific, but I should say there are certain scenarios in which we like to use dy dx, certain scenarios where we like to use df dx, and certain scenarios where we like to use f prime of x. And even with one more, there are even certain scenarios where we like to write probably the most cumbersome of them all, the most handwriting at least, and that's verbally said d dx of f of x, a derivative of f of x. And sometimes that's useful. We'll see where each of these are more useful than others. You'll notice that I'll just kind of use all of them in different scenarios. It really just depends. And so we'll see that. For the most part today, I'm going to be using this. And then later in the course, we'll see dy dx a lot more often. But just know that if you see any of these four things, those all mean the same thing. They all just mean the derivative of f. All right, so let's go ahead and start talking about the idea of taking multiple derivatives. So we've seen a lot about, hey, here's a function, take one derivative. But what's stopping us from taking even more derivatives, right? What if I had a function that was already f prime of x, and what if I took a derivative of that? Well, I would get another derivative. I would get the second derivative. It'd be another derivative. And so basically you could think about this. You could go on forever with this. You could start off with a function. You could take a derivative to get f prime of x. You could take another derivative to get f double prime of x. And again, that's how we verbally say this guy. We say f double prime of x. There's two tick marks. We could keep going. We could take a third derivative if we felt like it. F triple prime of x. And that's just saying I've taken a derivative of the derivative of the derivative. We could keep going like this forever. Nothing would be stopping us from doing that. But when we continue to go on like this, the notation will change a little bit. And so we want to be careful here. So let's say we start off with a function f of x, just like a normal good old function that we've seen. And I tell you, hey, start taking derivatives of it and don't stop. Well, as you might expect, we're going to end up with f prime of x here. And an alternative way to write that is to write df dx, as we saw before. Well, the moment that I take a derivative of that, I end up probably pretty clearly with f double prime of x. Hopefully this notation makes sense. It's just indicating 1, 2 derivatives here, whereas down here it'd be 1, 2, 3 derivatives. So we'll take a derivative of that derivative and we'll get f double prime of x. And here's where the notation on the right side gets a little bit more confusing. Instead of writing df dx, we kind of just throw these 2's in here. And the location of these 2's is important. I'm not really going to get into why we like to put, a 2 here. They almost look like squares. I'm not really going to get into why that's the case, but just know that this is sort of the notation. So if you want to use this type of notation on the right-hand side of the screen, and you're talking about a second derivative, you're gonna look right here. You're gonna have d squared f dx squared. We even use that word squared, which again can be a little confusing, but that's just kind of how mathematicians do it. If we kept going on and we took a third derivative of this function, so we took a derivative of the second derivative, yet again we're gonna have d cubed f dx cubed, and that's sort of how this is verbally stated. It's that df dx format, but we have those 3's there. And now here's where things get a little bit different, where they change up on us. If we go to the fourth derivative, basically mathematicians have decided that writing out f prime 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 of x is just too much work. It's too much writing, and so they just instead use this number written in the parentheses to indicate the derivative. This would be very helpful if you had like the 72nd derivative of x, because no one wants to sit here and write f prime 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 and just continue going until you hit 72. That's bad. That's just a lot of tick marks. We don't want to do that. So once we get to the fourth derivative, we'll start to use this sort of number notation here. One useful thing with this df dx type notation is that nothing changes. It just keeps going. I could continue all the way up until I had d72 f dx 72, and you could keep on going if you wanted to. But this is kind of your notation of multiple derivatives here. So this idea that you can take a derivative of a derivative and you can just keep going on forever and ever. So now that we have this idea of notation, as well as multiple derivatives, let's look at taking derivatives quickly. So like I said before, we've talked about the limit definition of the derivative, and we've seen that can be quite a bit of work. It's a lot of algebra, and we got to think about indeterminate forms with limits, and we got to do all that stuff. But what we're going to start to see now are much faster ways of doing these. And so what I want to start right off with is what I'm going to call the constant rule. Just make a note here, I am going to talk about the constant property later. Those are very different things. This constant rule talks about when I have a function that is just a constant. So an example of this would just be f of x equals 2, or maybe I write y equals 3, or maybe I write f of x equals 0. I can write any of these things, and those are all just constants. If you were to graph these, they would just look very, very simply like that, just a straight flat line. If we were to graph these on a graph. And so in this case, you're welcome to do the limit definition of the derivative, but what you're always going to find, if your function is a constant there, then you're just going to get 0 every single time. I definitely encourage you to try this. Try a couple examples of the limit definition, or a couple examples using the limit definition, where you just have your function as a constant, and I guarantee you're going to get 0 every time. And so what we'll say here, not really regarding the notation, I'll just say the derivative of a constant is 0. right? And so anytime you see a constant and you're going to take a derivative of it, you're going to get 0 there. Now, notationally, what I'm saying here is if I have a function f of x, then f prime of x, which is the derivative, I can say f prime of x, which is equal to, it means the same exact thing as d dx of k, which is my function, right? So this right here is just another way of writing the derivative of my function k, my constant, and that just ends up being 0, okay? So f prime of x is 0, and there we go. And so if this notation here with this d dx of k is confusing, I'd say ignore that just for a second here. On our next example, it'll be a little bit easier to look at, and I'll kind of explain why we might want to use that notation. So we've got the derivative of a constant is just 0, and we can move on from there. So now let's go ahead and look at the derivative of a polynomial. And this is called the power rule, and you'll see here that we're really going to be dealing with the power of my function. So if I have a couple examples of functions that this would apply to, if I have something like x squared, or maybe if I have something like y equals x to the, or let's say square root of x, right? Because this would be like x to the 1/2. This would work. This would fall under this format of this x to the n that we're looking at for our function. I could have f of x equals 1 over x cubed, right? Because I could rewrite this as x to the -3. And again, that falls under this format. So if you see a function that looks like x to the n, so i.e. x squared, x to the 1/2, x to the -3. If you see a function that looks like that, then you can take its derivative very quickly. And so we'll go into this notation here so I can explain what that derivative actually is. So here's my function f of x right there. Let's go ahead and box that in red. So I've got my f of x equals x to the n. So my f of x is that. If I want to take a derivative, I'm going to call that f prime. And then this is my answer for the derivative. I'll explain why that's the case in a second, or how we get to that. But this is my derivative f of x. Another notation for this is to say d dx, which just means derivative of x to the n. And this is why this notation here is super helpful, because I can very explicitly see what my function is, right? I can very easily see, hey, the function that I'm talking about is x to the n right here. And I've got my x to the n, and I'm taking a derivative of it. If I were just to write f prime of x, you have no idea what f actually is. If I were to write df dx, you still don't know what f is. But if I write d dx of my function and I actually write out what it is right there, then you can see, hey, that's my function. I know what I'm taking a derivative of. And so that's the only reason I use this notation here. Popping back to that constant, again, that's the same thing here. If I just cover this up right here, and let's say I covered up the function as well, you would just see, hey, f prime is 0. You don't know what my function is at that point. So here, same exact thing. If I covered this up and I covered up my function, you don't know what your original function is here. Alternatively, if I cover up what the function is and I cover up f prime, you can very easily see right here that I have my function right there, x to the n, that I've circled. And so that I'm taking a derivative of this x to the n, and that's what that sort of gives us a lot of information just with a simple notation change. So if we have a function that looks like x to the n, then we're going to sort of, I always use the word flick off the exponent there. So I'm going to take that n and I'm going to drop it down. I'm going to kind of flick it off the top and I'm going to bring it down to the bottom. And that's why I have it written out in front here. And then I just subtract 1 from that exponent. So we'll do several examples of this in just a second. But maybe a simple example right here, right off the bat, is if I had f of x equals x cubed, then what I could do is I could say, hey, f prime of x is equal to 3 So that's me sort of knocking this 3 down to the front. I have my 3x to the 3 minus 1, which I could simplify to 3x squared. So what you notice what I'm doing is I'm just taking this exponent, I'm dropping it down to the front, and then I'm just subtracting 1 from that exponent. So I get 3x squared. And obviously this is much quicker than doing the limit definition of the derivative. This will save us a lot of time, but we definitely have to practice on it and get good at it so that we don't have to fall back and revert to the limit definition. So let's move on. I want to talk about this constant property for derivatives before doing a couple examples. And so let's look at this. And again, this is different from the constant rule. The constant rule is when your function is a constant. This constant property talks about if I already have a function and I multiply it by a constant, what I'm allowed to do is I'm allowed to basically ignore that constant. I can take a derivative of the function as I normally would, and then I can just multiply it by a constant. So here's this notation again. We've got d dx of kf of x. So I have d dx of, oh, I don't know, let's just come up with an example of 3 times x cubed. Great. So what I'm allowed to do here is like I said, I'm allowed to kind of ignore, let me change these numbers here just so I don't have multiple 3s. Oh, sorry there. So I've got my, let's say 4x cubed. So basically, like I said, I'm allowed to forget that 4 for a second. And really what that entails is me pulling this 4 out front. You can notice here that I have that k that just kind of gets pulled out front. It's almost like you know, I can take two things and multiply them together. I can just, like, you know, separate them, if you will. So what I'm going to do is I'm going to pull this 4 out, and then I see d dx of x cubed, right? Well, what I can do here now, I can just take the derivative of x cubed, and good thing we actually did that back here, right? We got that 3x squared. So let's just go ahead and put that right in. I've got 4 multiplied, I'll just use a dot, by the 3x squared. So we already evaluated d dx of x cubed. So this guy right here, we already evaluated it to get 3x squared, and I just have my 4 right there carried over. At this point, we can simplify. We just get 12x squared, and that's our answer. And so all we've done there is we've just kind of ignored that 4. We've taken our derivative of x cubed like we normally would with the power rule, and then I just multiplied it by whatever that answer was by 4. And there we go. We get that answer. So that's this constant property. We're going to see an example of this next. And honestly, if this feels confusing right now, check back in with yourself at the end of these examples, but really, we're going to do so many of this. This is going to become so second nature that you won't even think about this constant property. The words constant property will never even pop into your head. You're going to get so good at doing this. So let's go ahead with an example. I've got 7x to the 4th, and so I want to take a derivative of that. So first thing that we should recognize is that I want to do the power rule, right? Because the power rule is for anything that looks like an x to the n, right? And I see that I have an x to the 4th, so that's going to indicate a use of the power rule. But you might say to yourself, well, Ryan, let's pop back to this slide here. Look, you told me that it has to look like x to the n, but you didn't say anything about a constant in front of it, right? And I have a 7 right out front. Well, that's exactly where this constant property is going to come in. I can basically forget that 7 for a second, and I can bring it back in at the very end. So let's go ahead and write out all this work here. So if I have f of x equals 7x to the 4th, what I can do is I can say f prime of x is going to be equal to 7 multiplied by just whatever the derivative of x to the 4th is yet. I'm not actually doing it yet. I'm just saying that I have to take the derivative, right? You can see this sort of mixing of notation that I'm using. I'm saying, hey, my derivative is equal to 7 times whatever my derivative of x to the fourth is. And that's me using the constant property there. So now on this d dx of x to the fourth, this derivative of x to the fourth, I can just do the power rule as we've seen. So when I do that power rule, I still have my 7 out front. And when I do that power rule, I'll put this all in parentheses so we can keep it separated. I'm going to drop that 4 down, and then I'm going to subtract 1 from it. And so when I do that, I get 4 that drops down, x to the 4 minus 1, which is obviously just going to be 3. And now this is just 7 times 4x cubed. So I can just I can go ahead and just simplify that. The 7 multiplies by the 4 to give me 28, and then we're just done. We get 28x cubed right there. And so yeah, so that's fantastic right there. We've used our constant property. We've used the power rule as well, and we've gotten our answer there. I've got typed up a slightly different way of doing this. You don't have to use the constant property right off the bat. You could look at this and say, hey, the derivative of f of x is just going to be d dx of 7x to the fourth, right? 7x to the fourth, this is my function, f of x right here. So if I take a derivative of 7x to the fourth, that's going to give me my answer. And so what you could do is you could take this 4 and you could drop it down out front. And that's what I've done over here. That's the 4 out front. Then I could subtract 1, and that's exactly what I've done right there. And now I just have the 4 times the 7, and I've got my x cubed right there. And you'll notice you get the same answer, obviously, but just a slightly different way. Here, I haven't actually used that constant property. I've just kind of carried the 7 through. I just kind of keep copying it down and keep writing it over and over. And you know, we just kind of forget that it's there and just keep copying it down. So there's a simple example of the power rule. We're going to do one more example, but before we do that, I want to actually talk about one more property for derivatives, and these work for any derivatives. So we'll say the sum and difference property. And this is just saying that if I have 2 different functions and I've added or subtracted them together, I can take a derivative of each of them and add them or subtract them together. So if I have my whole function that's just, you know, maybe 7 plus 2x. So let's go ahead and write that out. I'll write out this example. If I want to take the derivative of 7 plus 2x, what I can do is I can just do each of these separately. I could take a derivative of 7, and I can add to that a derivative of 2x. And that'll give me my answer just fine right there. So let's go ahead and do an example here. So we're going to keep using the power rule. That's all we've really learned so far, is that power rule. So here you can see that I have 2 distinct parts here that are being subtracted from each other. So really all that's saying is that when I do my derivative, just take a derivative of each of them and then just subtract those answers, right? So let's go ahead and go on with this. I've got f of x equals 1/2 x cubed minus 1 over x squared. I want to rewrite that though, because that to me does not look like the power rule. It looks kind of funky. So I'm going to rewrite this as x to the -2, and that's just me taking this 1 over x squared and just rewriting that with an exponent right there, with a negative exponent. And so at this point here, I can use my power rule as well as a couple of those derivative properties that we've been seeing. So if I go ahead and do this, if I take a derivative, let's go ahead and just say, okay, I'm going to look at the 1/2 x cubed. Let's take a derivative of that. So like we've seen with the constant property, I can kind of ignore that 1/2 and I can just take a derivative of x cubed. And so that's that constant property that I'm using. I'm just pulling out that 1/2. I'm just kind of forgetting about it, leaving it outside. And then the sum and difference property, it tells me that I'm allowed to just subtract whatever the derivative of x to the negative 2 is. Basically, I can just do these individually and then subtract my answer. When I say these, I mean each of these derivatives here. I can just do each of them. So we'll continue on. Using the power rule for this derivative of x cubed here, we've actually done this already, but using that power rule, we're going to have 3, which is me dropping this 3 down, and then I'm going to subtract 1 from it. So I'm going to get 3x to the 2. And so that 2 is from me doing 3 minus 1 in the exponent. I'm going to subtract from that. Now we got to be a little careful here. I want to take this negative 2 here, and I want to drop it down. So when I drop that negative 2 down, I'll put it in parentheses just so we make sure we don't write double negatives there. Now I am going to write x, and I need to subtract 1 from here. And so off to the side, I've got negative 2 minus 1, and that's equal to negative 3. So I actually want x to the negative 3 right there. At this point, we're pretty much done, but we want to do some simplification here. I can actually multiply the 1/2 and the 3 out. I'll have 3/2 x squared. The negative, or the minus negative 2 is going to give me positive 2, and then that's an x to the negative 3, so I can rewrite that without the negative exponent as over x cubed. So I'd have 2 over x cubed there, and that's just some algebra that hopefully we're comfortable with. So I get my answer right there, and this is great. We've taken a derivative of this kind of ugly function. Honestly, if we had to do a limit definition of the derivative for this, that would be very annoying, plugging in x plus h's, cubing them out, having to deal with a bunch of common denominators. It would get really ugly really quickly. But here we were able to just use the power rules as well as a couple properties, and we got our answer there. So just a recap of what we've done here. I've kind of ignored the 1/2 and the minus sign, and I've just kept carrying those down using those properties that we've talked about, the constant property and the sum and difference property. I kind of just keep bringing those down. I'm basically just taking a derivative of the main part here. And so when I do each of those derivatives of the main part here, I'm just utilizing the power rule. And that power rule says that I can drop the exponent down, and I can subtract 1 off of that exponent, and that's my resulting derivative. We obviously want to rewrite it without negative exponents. We started in this form that had no negative exponents. We had to edit it a little bit, but then we want to make sure that we go back to having no negative exponents. And so there we go. We get our answer there. The last thing that I want to mention here, so we've talked about the constant property, and we've talked about the sum and difference property. And I want to mention something that a lot of people think is a property, but it's actually not. So I always like to ask, hey, is this true? If I have a function and I square that function and then take a derivative, is that the same as me taking a derivative of that function and then squaring it? And it's actually not true. It actually doesn't work out. This does work for something like a limit, but it doesn't work for derivatives. And you can try this with x cubed, right? As we saw, a derivative of x cubed here ends up being 3x squared. We've done that example a couple times already in this lecture. So what you can check is actually just plugging in appropriately, and you'll see exactly this. So let's say that I did here. Let's put this on a different slide, and I'll show out this work carefully. So if we've got, so I'm gonna do the left side first. So f of x is equal to x cubed. That's good. So let's go ahead and do the left side. D dx of f of x squared. Well, f of x squared is just x cubed, and I got to square that. So d dx of x to the 6th, right? Because if I square x cubed, I get x to the 6th. Now, my power rule says that I drop that 6 down, and then I subtract 1 from that exponent there. So I get 6x to the 6 minus 1. which is equal to 6x to the 5th. And that's my answer for the left side. So we'll kind of box that and keep it off to the side. So we better hope that if we want this to be true, or if we think that this is true, we better hope that we get 6x to the 5th when I evaluate the right-hand side. And let's go ahead and do that. So I'll evaluate that right-hand side. And when I do that, we'll see what we get. So d dx of f of x, and then I'm going to square it. So here I'm taking a derivative first, and then I'm squaring it. Before I squared it, and then I took a derivative. So if I do d dx of x cubed, that's our function. We've seen before, we've already done this, we get 3x squared, just using the power rule, and I'm squaring that. So if I square this, I get 9x to the 4th, and that's really not even anywhere close to our 6x to the 5th. So clearly this is one example of how it doesn't work. So we can just say that in general, this actually does not, this sort of idea, this exponent property, if you wanted to call it that, it doesn't actually work. It's not actually a property. You can't square a function and then take a derivative and have that be the same as taking a derivative and then squaring the function. So that's going to kind of wrap up derivatives with their notation, properties of derivatives, and as well as the constant and the power rules. Just try to maybe look back at this example here. Try it again. This is a pretty classic example that we'll see, and we'll have a lot of problems like this on the worksheet. So I'll go ahead and leave it there for you guys.